So we were discussing the two-level system, and we started with a Hilbert space with a basis given by these two states, and we had discussed this Hamiltonian to give dynamics, to describe the dynamics of this two-level system, where, just for a reminder, let me write down these Pauli matrices. They are defining, these are the components of these operators, sigma 1, sigma 2, sigma 3, in this basis. And since these matrices are Hermitian, so they're defining Hermitian operators. So we took this as the Hamiltonian. Then this Hamiltonian is just a multiple of this guy. So that means this would be this matrix. So since it's a diagonal, that means the eigenvalues are E and minus E. There are two eigenstates for the Hamiltonian, and they have energy E and minus E. Now, suppose if I have, if I change the Hamiltonian, I have to give a dynamics, and as I said, to give the dynamics, by giving a dynamics, I mean I have to describe how the states change over the time, and that I can do by giving any Hamiltonian. If I'm defining the dynamics through a time-independent Hamiltonian, then this would be the time translation, time evolution operator, where this is a fixed Hermitian operator. So I'm just now choosing a new one. You just really choose one Hermitian operator over here. So let's choose this to be E sigma 1, let's say. And we know we had computed that sigma 1, its eigenvalues are, again, plus 1 and minus 1. So since this H is just a multiple of it, so this H eigenvalues are plus 1 and minus 1, 2. Oh, sorry, plus E, there's just scaled by that multiple, plus E and minus E. And the sigma 1 has, we also computed its eigenstates. So there was this plus. And in terms of the old basis, is given by this. And there was this minus given by this. So we have that H on plus gives the positive, and H on minus gives the negative. Now suppose if I have this dynamics and I start with the state up at t is equal to 0. So that means at this time, if I measure sigma 3, this is the eigenstate of sigma 3 with eigenenergy, with eigenvalue 1. If I measure sigma 3, I'm sure that I'll get 1 at this time. But what happens after some time? How does it evolve? this state becomes, you just have to apply on this state. How will I compute this evolution? Well, I can write this in terms of the eigenstates of H. And once I have, then I can apply this Hamiltonian, because then it's diagonal in that basis, and I can simply exponentiate the eigenvalues to get the answer. So from here, if I add them, I can find that this is just this. These will cancel, the downs will cancel, so I can compute this. Similarly, this would be this. These are all normalized, so you can note that. So that means this acting on this state can be written like this. And I know the action of H on this. We had actually discussed it in general. Like these are if you expand any state in terms of the eigenbasis, then you can simply write down the time evolution very easily. When this Hamiltonian will act over here, it will just pick up the corresponding eigenvalue, and you just get an exponential over here with the energy eigenvalue associated with this state. So over here, we only have 2 in the expansion. So we get, let's write it outside, e to the minus I t e over h bar plus e to the plus I t e over h bar minus. So that would be state after some time. And since this is not the starting state, was not the energy eigenstate, this is not a 10 energy eigenstate. So that means not a stationary state. So probabilities will depend on time. So for example, so I started with 100% probability of measuring sigma 3 to be 1. So we can now compute what is the probability now. So probability at time t is, you just take, so you're asking it for sigma 3, and you want to check for measuring +1. So you pick up the corresponding eigenstate, which is up, and just compute. So this probability would be mod square of taking this eigenstate and making its scalar product with your current state. And the current state is the state you started from, whatever its current state is after time t. So you started here, but in the Hilbert space, because of the time evolution, is going to some other state. And we are denoting it as this t, this mod square. That's the probability. So we can compute this So all I'm doing, I have this state. I'm hitting it with the up arrow. And this I can easily compute because I have the expression of plus in terms of these up and down state. So like over here, when I hit with up, this gives me 1 over under 2. But when it hits this, gives me 0. So for the first part, I get the answer 1 over under 2. This one also gives me 1 over under 2 because I'm hitting the minus with an up. So it picks 1 over under 2 here, and this doesn't contribute. So it gives me h bar plus over 2, which is sine of et over h. Well, not really. I need to bring in an iota. So iota here. Well, wait. Did I get plus or minus? Let me see. So I hit with the up. Here I pick plus, I pick plus. So I don't need to make it a sign, it's a cos. So it's cosine of et over h, and the probability is the mod square. So it will not remain in the up state. When I will measure, I started with the plus, but because with the up, but since it's evolving according to a Hamiltonian, which does not have this state as its eigenstate, so the probabilities keep changing. And after some time, if I measure the probability of getting this state back, +1. So remember, I can also say getting this state back, because once I measure +1, at that moment, whatever the value is of the state, that drops to this state. So you can use this language too. Instead of saying what is the probability of measuring +1, which is the more accurate language, but you can equivalently also say what is the probability of getting this state in the measurement. So you started with this. After some time, if you measure it, you don't get this back. You can, but only with a certain probability. And according to this, the probabilities are going between 0 and 1. If you catch it at an appropriate time, you are certain that you will get it back. And there are some times where you are sure that you won't get it at all. And actually, if you measure sigma 3, for sigma 3, there are only two possibilities. Of the outcome of measurement. So what are those? So we are just applying our postulates. According to the postulate, the possibilities are +1 or -1. So equivalently, you can say when you measure sigma 3, either you will find up state or you will find down state. The probability of finding up state after time t is this. So what should be the probability of finding down at time t? The probabilities must sum to 1. So that has to be this. But we can check with our postulate. So this probability, if I compute, it's the down matrix element. So when I do this over here, down hitting plus will give me 1 over under 2. Down hitting minus will give me minus 1 over under 2. So this is the state. I hit it with down. On plus, it gives me 1 over under 2. On minus, it gives me minus 1 over under 2. So this gives me 1 over under root 2. The first is e minus iota et over h bar, 1 over under root 2, minus since it's a minus, so I have to make it 1. And this becomes, if I take out a minus outside, over 2. But for the sign, I need an iota. I can just put over there. But this doesn't matter because to compute the probability, I have to make the mod square. So it gives me which I was expecting. Now, again, if I measure sigma 1, so I have what is the probability of getting 1 for the sigma 1 after time t? So this is the state which you are doing with this. So remember, this state turned out to be plus e to the plus iota so it's going to give me 1 over under root 2. This plus, its plus gives me e to the minus iota et over h bar, plus its minus gives me a 0. And this whole thing has to be mod square. So this is just half. The probabilities for plus are very different. At any time, probability of sigma 2 being 1 is same as sigma 2 being minus 1, and they are half. They're not changing with time. And that is because this time the Hamiltonian is an eigenfunction, is just a multiple of sigma 1. If you measure, so if this is your state, I know that the probabilities are, the state is evolving with time. and it has equal probability of getting +1 or -1 for sigma 2. If I measure under the measurement, suppose sigma 1 is not sigma 2, it's sigma 1, gives me, let's say, minus. That would mean right at that moment, the state will collapse to minus. And this is an eigenstate of Hamiltonian. So after time t, this will evolve at a later time t, just as e to the minus iota, e to the plus iota, t over h bar. Now it's a stationary state. Now if I do any of these probability of sigma 3 being 1, for example, at time t, doesn't matter, this drops out. So this is half. On the other hand, if I had, for this state, if I had measured sigma 3 and found to be, let's say, -1, then this state would collapse to minus. And this minus, this evolves under t to this operator. This is the minus, this state written in terms of the eigenstates looks like this. So this becomes now the probabilities of measuring. So this is at time t. Probabilities will again start changing. Let me just give you, just for practice, another dynamics. Suppose Hamiltonian this time is this. This is the original Hamiltonian which I took yesterday and I discussed in the very beginning, and add to it this, another piece which is proportional to sigma 1. There is still, you add to Hermitian operators, it's still a Hermitian. So I can add and make a new Hamiltonian I like. Actually, in general, I can add any one of them. And for any choice of these numbers, real number, they have to be real number for the operator to remain Hermitian. I'll get a Hermitian operator. And as we discussed last time, since these four matrices generate are the basis for the space of Hermitian matrices 2 by 2. So this is the most general Hamiltonian you can write. Actually, in 2 by 2 case, you can solve this Hamiltonian. By solving, you mean you can find the eigenvectors and eigenvalues. And once, as we had discussed last time, once you know the eigenvectors and eigenvalues, you can write down the dynamics for any state. You can evolve any state, you can, starting from any state, you know how to write the action. All you have to do is expand that state in terms of the eigenbasis. And since this time evolution operator acts diagonally over here, so So you pick up just the eigenvalues and you know what would be the state at a later time. So you can completely solve the dynamics for any Hermitian operator for the 2 by 2 case. Well, actually, if you have a finite dimensional system, then in the end, your dynamics involves diagonalizing n by n Hermitian matrix. Because all you will be doing, finding the eigenvalues by diagonalizing it, and when you diagonalize, you can also compute the eigenvectors. So you can expand any state in terms of the eigenvectors, and then you can tell what will become of the state after some time using this operation. So solving the dynamics is completely equivalent to diagonalizing the Hamiltonian. And in n by n case, you can always do it. It's just a matrix problem. If you can't do it by hand, a computer can do it for you. It's just about how much computing resources you have. But in the infinite dimensional case, many a times computer cannot, well, at least it won't give you the exact results. Then you are in the arms of solving differential equations because you have infinite degrees of freedom. But in any case, let's take this example. So the Hamiltonian is E sigma 3 plus delta sigma 1. And if delta is small in what sense? Later on in course, we will make it clear. But over here, you can say delta is smaller than E, then it is called a perturbation. But we don't have to call it because we don't need to assume that it's small. It's just a 2 by 2 thing. We can exactly solve it. So this matrix becomes minus E. And if I compute the eigenvalues, I get this. Let me call the eigenvalues E plus. So it's E square minus delta square is equal to 0. So that gives me, that's the determinant. So, well, let's me write lambda first to make it a little bit clear. This is the determinant I'm computing. So I have E minus lambda whole square minus del square is 0. So wait.
सर वो नीचे माइनस ई माइनस लैम्डा नहीं होगा?
Yes, that's what's going on. Yeah, those were not the eigenvalues I was expecting. So I get E minus lambda minus E plus lambda minus del square is 0. Am I right? E square minus lambda square minus del square is 0. So lambda square is E square plus del square. So that means the eigenvalues are plus minus E square plus del square. So that means the two energies, the eigenvalues are just the energy eigenvalues. I was solving it for the Hamiltonian. So there's this. And there's this. and actually E plus let's say E minus is just minus E plus. Now, what are the eigenvectors? So I can solve this equation for both of them one by one. So I'm after these, but I'm solving them in a particular basis. And in this basis, I can write it as a matrix equation. H is just these matrix elements. And I'm finding the components of psi. This is the basis I'm writing all these equations in, up and down. So the first eigenvalue is this, and that gives me EA plus delta B is E square plus delta square A, and that gives me B equals to minus A delta square, yeah, over delta. Now, whenever you solve for the eigenvectors, because we know that any multiple of an eigenvector is still an eigenvector with the same eigenvalue, because eigenvectors, they at least span, even if you have non-degenerate eigenvalues, like in this case, every eigenvalue occurs only once. So we have non-degenerate eigenvalue, but still you have at least one-dimensional space spanned by your eigenvectors. So this is one eigenvector, the other is orthogonal to it, other one. So we can scale it. So A and B, I find B in terms of A, but the overall scale is arbitrary. So I want to fix some of it, as always, not as always, but as most of the time is very useful to do it, because when you are, as we discussed, when we are using our probability formulas without dividing by anything, we must normalize our vectors. And for the eigenvectors of any operator, you should always normalize them, because these formulas, the probability of finding an eigenvalue A, they work even if I'm not normalizing psi. These eigenvectors must be normalized if I'm not dividing by any norm of A. This formula will work only if eigenvectors are normalized. So let's normalize these eigenvectors. So what's the normalization of the eigenvector? Eigenvector is this thing. So that means this plus eigenvector is this. So its norm is A mod square plus B mod square. You can compute it, or if they are orthogonal, which these two guys are, then you directly know that it's going to be the sum of the mod squares. So this I want to put equal to 1. So apart from this condition, I should also put in this condition. So what does this condition gives me? It gives me A square. For B, I put in this thing. And that gives me A mod square is equal to 1. it this way. E over delta now I just want to parameterize it in a particular way, just to see things more clearly and being able to manipulate these some of the equations more easily. It's always a good idea to bring in known functions like sine or shine. So over here, since this del is less than, well, its mod is less than 1. Because del, I'm not saying is going to be is plus, is positive. It could be negative, but it doesn't matter. This guy, the thing in the bottom is positive, and this is going to be true always, because when, well, it's obvious if E uh, is 0, even then you get, wait, it wasn't minus, it was plus. That makes it more sensible. Well, only that makes it sensible. So right, it's a positive number below it, and whatever value E's take, or whatever value WR is going to be less than 1. You're just adding something positive to the denominator. So that means since it's between -1, it can only be between -1 and +1. So we can parameterize it with a sign. Take sine theta and take, if this is sine theta, then you want is 1. So that means cosine theta can parameterize this thing. That would be true, because when you add these, you get 1. So, but this would also mean that tangent theta is simply del over E. So therefore, if I look at this equation, this one, this is 1 over sine theta, and this is 1 over tangent theta. So I get, from normalization condition, I get A mod square plus A mod square sine theta whole square is equal to 1. And this gives me sine theta 1 minus cosine 1 plus cosine theta whole square is 1, and that gives me tangent square theta by 2. Let me check this identity. Double half angle identity. I'm just looking it up on Google. Sine theta over 1 plus cosine theta is,
सर ये cot नहीं होता?
ये cot है. I just looked it up. And let's see, what does this become? 1 plus cot square, what is that? Anyone remembers that?
cosec होता था शायद.
Wait. Cosecant is 1 over sine square theta. So A mod square is sine square theta. So what would be then B mod square? That would be
क्या theta by 2 आएगा यहाँ पे भी?
theta by 2. B mod square is then it should be cosine square theta by 2. But so you might be tempted to then write this thing. No, all these things have been reversed. I made a sign error in my notes, but I think in the end everything will work out. So we should not be worried. So let me write this down. So this eigenvalue has turned out, eigenvectors has turned out to be, I have to write A over here. So you might be tempted to write this thing. But this is not justified because all you got from here is A mod square and all you got here is B mod square. So for A, the best you can, this gives you A is equal to with some phase. And this gives you B is equal to E iota some other phase. Let's say delta. So this is not the right thing. I should be writing these phases. But I can multiply any vector with a pure phase and that does not change its norm. And I'm only normalizing it. My condition is only how to normalize it. So I can multiply it with an overall phase. So I can take one phase out of here. So for example, I can multiply with e to the minus iota gamma. This phase goes away. But I will have e to the minus e to the iota delta minus gamma phase here. So some other phase here. So I want to know what is this phase exactly. So that I cannot directly figure out from this equation. What was the equation? I should go back to the formula which relates B with A. There was a condition coming from the eigenvalue equation, which related B with A. So I should go back to that. I can fix the phase of any one of them arbitrarily. That's fine because that's equivalent to multiplying with an overall phase. The relative phase is important. So once you pick the phase of one, the phase of the other you cannot pick by yourself. That should come from this condition. So let's choose, let's give, so like over here, let's choose A is equal to sine theta by 2, picking this particular phase. Then B is, what was the equation? Wait, this one, minus A into E minus under root E square plus delta square over delta. Let me just check again. Yeah, minus A into E minus under root E square plus delta square over delta. So B is minus, for A, I have sine theta by 2. And, well, let me, and E over delta, I have E over delta minus, so this was called the, what was this? E over delta was tan or delta over E? So it's 1 over tangent theta. So that's cosine theta over sine theta. And this guy was 1 over sine theta. One over, yeah, delta over under root E square plus delta square is sine theta. Cosine theta minus 1. So now again I have to look one of these half angle formulas. Wait. Because the one which I have in notes is with the other sign.
The minus 1 upon cos theta by 2. Sec theta by 2. Minus sec theta by 2.
नहीं नहीं.
Minus common नहीं लेंगे.
Wait, where did they go in my half angle formulas? Yeah, sine theta by 2 is 1 minus cosine theta over sine theta.
Minus
1 minus cosine theta over sine theta is sine theta. So I can absorb the minus sign and it will give me sine theta by 2 times sine theta by 2. So I don't get any extra phase. Well, actually, I could have included a phase here to start with. This will just keep going. So that means in this formula, the phase of the two terms is same. So I can cancel the phase of both. Wait, what did we do? A was sine theta by 2.
सर
B,
ये sin theta by 2 divided by cos theta by 2 होगा.
ये?
That would हाँ
नहीं
ये
नहीं
यहाँ पे
नहीं 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 नहीं
cos theta minus 1 में हम minus common लेंगे and then it would become 1 minus cos theta which is equals to 2 sin theta by 2, right? And denominator में it would be like 2 sin theta by 2 cos theta by 2 which will make it 1 upon cos theta by 2. I think so. देख लें आप.
Let me see. So it would be ऊपर क्या आया? Cosine theta by 2.
सर नहीं देखिए -1 माइनस कॉमन लेंगे तो ये हो जाएगा 1 minus cos theta which is equals to 2 sin theta by 2.
अच्छा.
ठीक है. एंड नीचे डबल एंगल फॉर्मूला लग जाएगा तो इट वुड बी 2 sin theta by 2 cos theta by 2. तो sin थीटा बाई 2 तो कैंसिल हो गया ना न्यूमरेटर डिनोमिनेटर में. डिनोमिनेटर में सिर्फ cos थीटा बाई 2 बचा. माइनस डिसॉल्व हो गया तो sin थीटा बाई 2 डिवाइडेड बाय cos थीटा
मुझे
बाई 2.
एक एक कहने मुझे ना वो टेंजेंट का हाफ एंगल देखने दें. Okay. So this 1 minus cos theta, actually I read it wrong. So now this is right in front of me on Google, so I don't have to trust you. It says 1 minus cosine theta over sine theta is tangent theta by 2. One minus cosine theta over sine theta is tangent theta by 2. So it gives me, but that doesn't give me a very nice. I was hoping to have a cosine theta by 2 over here.
सर वो उसकी वैल्यू दिखा दें ए स्क्वायर ओवर डेल स्क्वायर. आई थिंक इधर 1 ओवर cos थीटा आना है sin थीटा की बजाय 1 ओवर sin.
इधर नहीं,
ये थर्ड लाइन में.
ये इधर नहीं नहीं
जी
नहीं, इधर 1 over cos theta तो नहीं आना. cos में e था. This was 1 over sine cosine theta minus. Could this be that our a could be making a mistake, that a could be cos? One plus cos theta over sine theta is cotangent theta by 2, and cotangent theta plus 1 is what? Cotangent square theta by 2 plus 1, what is that?
स्क्वायर थीटा.
Secant,
स्क्वायर थीटा.
which is the inverse of sine or cos?
cosec is inverse of
Cos.
sin. sec आ रहा है
cos
Cotangent
secant
square.
cos का होता है.
cosec जो है वो sin का होता है. cosec क्या हो
एक
गया?
मिनट है ना.
सिर्फ 1 plus tan स्क्वायर थीटा इज इक्वल टू
Yeah, well, this is how it's turning out to be. So what I'm gonna do, I'm pretty sure that there's some sign error, which is not giving it a very nice form. Well, this cannot be true. Yeah, this cannot be true because this is giving me for B sine theta by 2 square over cosine theta by 2. And we have been deriving it using this. So that doesn't give me this. So we are making some mistake. B has to turn out to be cosine theta by 2, right? So what is the mistake? E over delta is cosine theta over sine theta. 1 over sine theta. B is minus E plus I think that was the mistake over here. See? Over here, someone should have reminded me. This plus sign, if I look over here, this equation is coming from this equation, right?
Hmm.
And the relative sign is not plus, it's minus. So it's 1 minus cosine theta over sine theta, which makes it tangent square theta, right? Because that's the formula I just read off from, and that's also how it is in my notes. So it's 1 plus tangent square theta, which gives me 1 over cosine square theta.
नहीं sec.
1 plus
Tangent.
tangent square theta by 2 is 1 over cosine square theta by 2.
Okay, sorry.
So A mod square is cosine square theta by 2. So B mod square should be something like sine square theta by 2. So first one has cos, second one has sine. Cos, sine. So A is cos, so B is sine theta by 2. And with the same phase, whatever the phase of A is the same phase for B. So there is no relative phase. So I can just cancel this whole phase. And I know that this is a completely fixed expression with normalization plus down. I can still multiply it with any phase. That you can always do. I don't need to. So this is a acceptable form for this eigenstate. And the other one, I can try to compute it. I will have to go through all this algebra, but I don't really need to do it because I know these properties that since these are two separate eigenvalues which are distinct, so these two states must be orthogonal. And the other state also I can make it normalized. So to make it orthogonal, I will have to make it this way. Because when this will hit this, it will give me cosine theta by 2, sin by theta by 2. When this will hit this, it will give me cosine theta by 2, sin theta by 2. When this will hit this, it will give me sin theta by 2, cos theta by 2 with a minus sign. So it will be 0. So I know that this is the correct expression and it's properly normalized. I cannot put a plus sign between them because that will not cancel. So this is the unique expression I will have. And from this expression, if I want now, I can write the form for this as well. All I have to do is multiply this guy with cosine and this guy with sine and add. Right? So because if I multiply with this cosine, this with sine, and add, these down ones, they drop out. And then I have cosine square theta plus sine square theta, that gives me 1. So I do not get anything in front of this guy. And from the right hand side, I just get these. So this is the inverse expression. And similarly, you can then guess that this would be guess or compute so now I want to cancel this, so I will have to multiply this with sine, this with cos. So e plus will come with sine and e minus will come with cos, and I have to have a relative negative sign between them. So these will be the inverse expressions. Now these guys, these are energy eigenstates. So you can evolve any of this state using this expression. So for example, you can ask the question, if you were in the up state, by the way, I think I didn't mention it, or maybe I did, just for imagination, I think I did. Why we call it up? This is the eigenstate of, you can represent this physical system where you have a spin, and spin along any axis can have only two possible values. Either it's aligned with that axis or it's, so this is the axis, z axis, let's say third axis. So either it will be aligned or it will be anti-aligned. You measure its projection along z axis, either it comes out to be aligned or anti-aligned. You don't get any intermediate projections. So that's why it's in the language people just call it spin up. So suppose you start with spin up, what happens to it after some time? That you can find out. Well, which one should I do first? Okay. So let's just compute it. What is this going to be? All of this is just for practice. So this is cosine theta by 2. I'm using this expression. All it does is picks up the corresponding energies in the exponent. E to the minus I E tilde over H bar and E plus. So E plus, for shorthand, just writing it at like this because I know that E minus is just this. It's the negative of that. Plus sine theta by 2 e to the iota E tilde that's what's going to happen. Each one of them is going to pick up their corresponding eigenvalue. Now I want to answer this question that after time t, what happens if I measure the probability of finding sigma 3 to be up at time t. So all I have to do is take this scalar product and square it. So when I do that, I get cosine theta by 2 plus now I have the expressions of these in terms of the spin up and spin down. What were these? This guy was down, while this guy was sine theta by 2 spin up minus cosine theta by 2 spin down. So from here, when this up hits, it just picks up the cosine. Does it pick up the cosine? Yeah. So let me, yeah. Over H bar. And when this up hits this, it picks up the sine. Now I have to do is mod square.
Sir, can you scroll up?
Yeah.
Sir, पॉजिटिव नहीं आएगा, प्लस नहीं आएगा बीच में?
Plus, wait. Yes.
Trust me, please.
Yeah. So when I do this, mod square, so then I have to do what? I have this guy. And then I make the complex conjugate. So when this hits this, I get cosine 4 theta by 2. When this hits this, I get sine 4 theta by 2. And when this hits this, I get plus cosine square theta by 2 sine square theta by 2 e to the minus iota et over h bar, and plus cosine square theta by 2 sine square theta by 2 e to the iota et over h bar. So I can take these common. This gives me a cosine of e. This is the e tilde. Right. Yeah. Now this guy, I think this is, what is this? This is, I should be able to write some nice thing for this. This is sine theta, right?
Yes, sir.
And what can I do about it? Cosine square. Wait. If I want to go from half angle, what's the double angle formulas? I don't want to waste too much time on these trigonometric, because what I did, I computed the wrong one. Well, the other one is easier to compute. If I had done this, that's easier. That has a very nice trigonometric identity, but we should be able to do it from here too. So that's sine theta, and cosine 2 theta is cos square theta minus sine square theta. So this can give me well, I'm just gonna leave it here. It should turn out give me a nicer formula, but it just gives you these theta are fixed. Thetas are theta is fixed by, because theta is just this thing. It was del over E. So whatever parameter you have picked is fixed by those. Whatever is the strength of the first part in the Hamiltonian, whatever the strength of the other one. However, this has this thing, cosine E hat E t over h bar, where E is just what you had computed, this thing. So depending on these parameters, and there's a time, this probability will again be sinusoidal. And so let me just leave it over here. We can probably give it a nicer form, but I don't want to now gonna waste time in looking up these trigonometric identities. But the point is that you can exactly solve it. You can solve these 2 by 2 or any n by n systems. 2 by 2 is easy enough to solve it by hand. And in essence, all you need is the eigenvectors of the Hamiltonian, and then the rest is just computing these scalar products, and you can get these things. So this sinusoidal, this is not the correct, the final thing we have right now. We should give it a nicer form, but this sinusoidal probability, this is, by the way, is also called the Rabi oscillation. But let me stop it here and move to another example. But let me take a 2-minute break. Okay, so I'll be back in 2 minutes. Well, before moving to example 2, there's something I wanted to say. So this two-component system, this is called a two-component system. Some people call it two-level system, because because it can describe two levels in any atom. If you concentrate on two levels, energy levels of an atom. So for example, this could be, the overall energy doesn't matter. You can shift them by any constant. So the difference matters. So you can call it minus E and this plus E. So this Hamiltonian can then be described by this. So it's just sigma 3, and the system is diagonal. This is in the energy basis, and the energy basis is just this basis. And then the other operators, if you just concentrate on these two levels, it's just there you have only these two states in your basis, in this particular basis, and the other operators are just linear combinations of these and this. So whatever we have been doing can describe a two-level system, two levels in an atom, a spin, or any system where you are only concentrating on two levels, two states, and the rest have been separated somehow. You're not concentrating on them. So this two-level system, it has a nice representation on a sphere. All states of a two-component system.
Excuse me, sir.
जी,
सर ये वो क्यूबिट्स जो होती थी वो ये वही होता है टू लेवल सिस्टम
हाँ वही two-level system है. So what's a qubit? Qubit is, wait, I'm saying something. What's a qubit? You have a state and it has two bases. So what's a bit? Bit is something which can be 0 or 1. So what's a qubit? Again, it's something which can be 0 or 1. But what do you mean by qubit? That means all linear combinations are also possible states. How do I get rid of this guy? Wait. Okay, it's gone. Yeah. So when you pick, so that all linear combinations are also possible state of a qubit. And this 0 and 1, they then become the basis states. So you can take this up to be 0 or down to be 1. It's exactly same. And then the Hilbert space of this two-level system is the Hilbert space of a single qubit. When you have more than one qubit, then you are taking the tensor product of these Hilbert spaces, and that's it, nothing more. So if if I call it 2 for two-level system, if you have many qubits, that's all you're doing. And obviously, किसी का mic open है? So you have these, but you can also write them as some other direct sum states, direct sum Hilbert space. So it would be some, I'm indexing them by something else. But to start with, you have just this tensor product. Now, all states, just wait, let me just wait for 1 minute. So all states of a two-level system, so all states in the Hilbert space, they are of this form. They can be mapped to points on a two-sphere, and then that two-sphere is called block sphere, and each point on that block sphere is representing one state in the Hilbert space. So how does it work out? A two-level system, or you can, as you had pointed out, you can say one qubit. All states of a single qubit can be represented by points on a two-sphere. So how does it work out? In your Hilbert space, you have all these linear combinations. But you know that there's a lot of redundancy which you want to reduce. First of all, you want it to be normalized. So that means if you have this condition, then you can always, this is a positive number, this is a positive number, two real numbers summing to give you something, you can parameterize them using one parameter. And in this case, you can parameterize them to sine and cos because their sum is 1. So from here, A takes this form, a sum phase, and B is this magnitude with some phase. So this is just coming from normalization. that psi can be written as but as we just discussed, the overall phase does not matter. We do not care about the overall phase. And let me just for emphasis, just uh, again mention why is that so. Phase does not matter. Why? Because if I will be computing probabilities, I'll be taking the scalar product of this my state with some eigenvector or some other vector. And then computing these things. So obviously, if I multiply it with an overall phase, in this drops out. So the overall phase does not matter at all in any physical prediction. So we define states as vectors in a Hilbert space up to an overall phase. So some people say that states of a quantum system are ways in a Hilbert space. What do they mean by that? They mean you take a vector, first you normalize it. So first of all, it's a normalized vector. But all of these guys are representing only one state. So I can multiply it with a phase, overall phase. So I multiply it by E minus iota delta. So I can remove phase in one of them. Completely equivalent statement to this is that only relative phases matter. Because they come in when you compute the scalar product, they do not go away. So this gives me sine theta E iota gamma minus delta down. So this phase I can call some noon phase. So this is the general form of my state. I can write any state in this form. Now over here, notice that if I change theta by theta plus pi, what happens? Psi goes to but this is just minus cosine theta, and this is just minus sine theta. So you have taken out an overall sign. But we are only defining this state up to an overall phase. This is just an overall phase. This is just e to the iota pi. So this is equal to, well, equivalent to psi. We are considering the equivalence class in some sense. So that means I should restrict theta to 0 to pi. Theta takes values only between 0 and pi. Well, if you want to be very exact, is something like this. So if your theta is between 0 to pi, but this can be phi is between 0 and 2 pi, because that every value of over there gives you a different phase over here, and there's a periodicity of 2 pi, so you don't need to go beyond that. So that means you have these two numbers, 0 to 2 pi, and phi, 0 to 2 pi. So you can map them on a sphere, because a unit sphere can be parameterized, or you can give it coordinates theta and phi, which you know are the usual coordinate. You, from the z-axis, let's say it's z-axis, you drop down by how much you drop down, by what angle, that's the theta, and then you can move around using an angle phi. So that gives you the coordinates on a sphere. So you can map the state. The state is described. State is completely characterized by theta and phi. So you can write state using this. You know theta, you know phi, you know what the state is. That's the most general parameterization over here of the state. And in this parameterization, theta has to be restricted from 0 to pi, and phi has to be restricted from 0 to 2 pi. But that means I can map the parameters of the state to a two-sphere. Parameters of state can be mapped to two-sphere. Well, there is still a problem. And what is that? Consider, so let's say, however, any angle which is, let's say, more than pi by 2. It can be written as, so there is, suppose, some line over here. This one, this angle. This is my theta. And this is more than pi by 2. So I can write it as pi minus theta dash, where theta dash is less than pi by 2. Right? So I can write it as I have this angle. This is total pi, and this is theta dash. So I come down by pi, and I go back by theta dash. And if I have to come back to a point which is at an angle more than pi by 2, I will have to go back by an angle less than pi by 2. So this would be true. So, but that means that if I consider this state, the state corresponding to this or anywhere on this wing, because I'm not even bothering about the phi angle. Phi could be anything. So corresponding state which is theta phi state where I know that theta is more than pi by 2. This, as I said, I can write it like this. Theta dash, some new angle, where theta dash is less than pi by 2. Now, what is this? Cosine pi minus theta. Well, this is just cosine theta, right? We can draw this. So you have this pi, this is pi. You're going back by an angle theta. This cosine, well, it's a minus cosine theta, right? So if this is theta, this is pi minus theta. So whatever cosine you have here, this is just minus of that. While for the sine, whatever you have same sign here. So there's a sign flip over here, but I can do this. Dash minus because e to the iota pi is minus, so this gives me an extra minus sign. And this gives me phi plus pi. An overall negative sign, I don't care. So this is the same state as so what does this mean? This means this state will be same as if I, instead of having this pi minus this angle theta, which comes up to here, and this is theta dash, I construct, I should use a new color. I construct a theta dash here, get this point, and it had a certain phi. I add to it a phi, a pi over that. So I will get a state which would be, my drawing wasn't very good, but it would be the diagonally opposite on the other side. But it would be on the upper hemisphere. That means this state, which is in the lower hemisphere, is same as this state on the upper hemisphere. So you can look at it this way as well. So, well, this was supposed to be like this. This angle is same as this angle. So you can just look at it that this is, if this was pi minus theta, and then you come back here. So this state is equivalent to this state. That means the states in the lower hemisphere are redundant. I don't need them. This state where theta was more than pi by 2 is same as this state where theta dash is less than pi by 2. So it's in upper hemisphere. You can compute what theta dash is. It's just pi minus theta. And then you rotate around to the other side on the upper hemisphere by an angle pi. So I can get all the states by restricting myself to the upper hemisphere. So that implies theta should be restricted to these values. Not pi. Even pi is not needed. Only 0 to pi by 2 is needed. So then it's a better idea to represent this like this. Instead of restricting theta to 0 to pi by 2, the above, so you kind of define a new theta, which is, and instead of above, you write it like this. Here, theta can range from 0 to pi, because this new theta in terms of the old theta, when you will go from 0 to pi, the old theta would be only going from 0 to pi by 2. Now you can map to the full sphere. So take this representation has the range without any redundancy. So now this can be mapped to the full sphere. And this is the block sphere. So for block sphere, this mapping with this representation, this particular where you have theta by 2, not theta, gives the block sphere. And you can see if I put theta equal to 0, what do I get? I'm on the north pole. So this is the upstate, or in qubit language, if you want to call it 1. And if I put theta equal to pi, what do I get? Cosine pi by 2, which is 0, and sine pi by 2, which is 1. And overall, so I just left with this state, this is killed, then this becomes an overall phase. It doesn't matter. And that's how it was on the sphere. On the north and south pole, you don't even care what is the phi angle. So this guy is then the downstate, or 0. What if you choose theta equal to pi by 4? Well, pi by 2. If you choose theta to be pi by 2 and phi to be 0, your state cosine, you are picking cosine pi by 4, which is 1 over under root 2, up, plus sine pi by 4, which is again 1 over under root 2, down, and e to the iota 0 gives you 1. So this is the plus state we were writing. So it's on the equator going this way. on the equator. While if I choose theta pi by 2 and phi to be pi, this will give me 1 over under root 2 up, 1 over under root 2 down, but e to the iota pi will give me a relative negative sign, which was my negative state. So it will be in the other direction, an addition of angle phi, rotation by angle phi, but on the equator. But then I had this guy. So this is the eigenstate. These on the north and south pole are the eigenstates of sigma 3. On the equator, directing in this direction, you can call it southeast, whatever. They are in the direction, or they are the eigenstates of sigma 1. I had actually this guy too, sigma 2, which was, let's see, was it minus iota or plus iota? Zero minus iota, iota 0. What are its eigenvalues? Again, they are plus and minus 1. And if I compute the eigenstate, it gives me, did we do it? So that gives me B is equal to iota A. So this thing is the normalized eigenstate with eigenvalue plus 1. And we can call them these. So this state, if I take theta is equal to, again, pi by 2 on the equator, but phi equal to pi by 2. So e to the iota pi by 2 gives me iota. So this state over here is on the equator, but then I move by pi by 2. So at 90-degree angle to the plus state. And then you can check on the opposite side is the one with the negative eigenvalue. So the other one with the other eigenvalue is this. So that's all for block sphere. And maybe so when do we meet next? Sometime tomorrow, can we meet?